Hello children, welcome to the Term 2 Science video session. In this video session, you are all going to learn the lesson Atomic Structure from Chemistry of Standard 8. Come, let's enter into the lesson. Interaction. Every substance in our surrounding is made up of unique elements. There are 118 elements identified worldwide so far. Out of these elements, 92 elements occur in the nature and the remaining elements are synthesized in the laboratories. Copper, iron, gold, and silver are some of the elements found in the nature. And elements like technetium, promethium, neptunium, and plutonium are synthesized in the laboratories. Each element is made up of similar minute particles called atoms. For example, the element gold is made up of gold atom which determines its characteristics. And we have learnt about the atoms in the earlier classes, isn't it? The word atom is derived from the Greek word atomos. Tomos means smallest divisible particle and atomos means smallest indivisible particle. Ancient Greek philosophers like Democritus have spoken about atoms. Even our Tamil poet Avaya has mentioned about atoms in a poem while describing Tirukkural. But none of them have scientific base. The first scientific theory about atom was given by John Dalton. Followed by him, J. Thomson, Rutherford, and Bohr have given their theory about atom. In this lesson, we will study how atomic theories evolved at different times. We will also study about valency, molecular formula, rules for naming chemical compounds, and balancing chemical equations. Come, let's enter into the lesson. Dalton's atomic theory. John Dalton provided a basic theory about the nature of matter. He proposed a model of atom known as Dalton's atomic theory in 1808 based on his experiments. The main postulates of Dalton's atomic theory are all matters are made up of extremely small particles called atoms. Greek philosopher Democritus used the same name for the smallest indivisible particles. Atoms of the same elements are identical in all aspects like size, shape, mass, and properties. Atoms of different elements have different sizes and masses and possess different properties. Atoms can neither be created nor be destroyed. That is, atom is indestructible. Atoms of different elements may combine with each other in a fixed simple ratio to form molecules. An atom is the smallest particle of matter that takes part in a chemical reaction. Advantages of Dalton's atomic theory. Dalton's theory explains most of the properties of gases and liquids. This explains the law of chemical combination and the law of conservation of mass. This theory helps to recognize the molecular differences of elements and compounds. Then, the limitations of Dalton's atomic theory. Atom is no longer considered as the smallest indivisible particle. Atoms of the same element have different masses and that is called isotopes. Example, in chlorine element there are two different atoms, that is chlorine 35 and chlorine 37. These are the atoms of the same element but have different masses like 35 and 37. Atoms of different elements may have same masses and that is called isobars. Example, sodium and magnesium. These are the atoms from the different element but have same mass 23 and 23. Substances made up of same kind of atoms may have different properties. Example, coal, graphite and diamond are made up of carbon atoms but they differ in their properties. Fundamental particles. In 1878, Sir William Crookes, while conducting an experiment using a discharge tube, found certain visible rays traveling between two metal electrodes. These rays are known as Crookes rays or cathode rays. The discharge tube used in the experiment is now referred as Crookes tube or more popularly as cathode ray tube, CRT. The cathode ray tube is shown in the picture. Now we are going to see how the cathode ray tube works. Cathode ray tube is a long glass tube filled with gas and sealed at both the ends. It consists of two metal plates which act as electrodes connected with high voltage. Look at the picture for better understanding. The electrode which is connected to the negative terminal of the battery is called the cathode. That is negative electrode. The electrode connected to the positive terminal is called the anode, and that is positive electrode. There is a side tube which is connected to a pump. The pump is used to lower the pressure inside the discharge tube. Do you know, electricity when passes through air removes the electrons from the gaseous atoms and produces cations. This is called electrical discharge. Discovery of electrons. When a high electric voltage of 10,000 volts or more is applied to the electrode of a discharge tube containing air or any gas at atmospheric pressure, no electricity flows through the air. However, when the high voltage of 10,000 volts is applied to the electrodes of discharge tube containing air or any gas at a very low pressure of about 0.001 millimeter of mercury, a greenish glow is observed on the walls of the discharge tube behind anode. This you can understand by the given picture. These observations clearly show some invisible ray coming from the cathode. Hence, these rays are called cathode rays. Later, they were named as electrons. Do you know the fact that air is a poor conductor of electricity is a blessing in disguise for us? Imagine what would happen if air had been a good conductor of electricity. All of us would have got electrocuted when a minor spark was produced by accident. Properties of cathode rays. Cathode rays travel in straight line from cathode towards anode. Cathode rays are made up of material particles which have mass and kinetic energy. Cathode rays are deflected by both electric and magnetic fields. They are negatively charged particles. The nature of the cathode rays does not depend on the nature of the gas filled inside the tube or the cathode used. Discovery of protons. The presence of positively charged particles in the atom has been precisely predicted by Goldstein based on the conception that the atom, being electrically neutral in nature, should necessarily possess positively charged particles to balance the negatively charged electrons. So Goldstein repeated the cathode ray experiment by using a perforated cathode. That means the cathode with holes. On applying a high voltage under low pressure, he observed a faint red glow on the wall behind the cathode. Since these rays originated from the cathode, they were called anode rays or canal rays or positive rays. Anode rays were found as a stream of positively charged particles. Do you know, when invisible radiation falls on materials like zinc sulfide, they emit a visible light. And these materials are called fluorescent materials. Properties of anode rays. Anode rays travel in straight lines. Anode rays are made up of material particles. What is meant by material particle? It has less mass and never travels with speed of light. Anode rays are deflected by electric and magnetic fields. Since they are deflected towards a negatively charged plate, they consist of positively charged particles. The properties of anode rays depend upon the nature of the gas taken inside the discharge tube. The mass of the particle is the same as the mass of the gas taken inside the discharge tube. Do you know? When hydrogen gas was taken in a discharge tube, the positively charged particles obtained from the hydrogen gas were called protons. Each of these protons are produced when one electron is removed from one hydrogen atom. Thus, a proton can be defined as an hydrogen ion, H+. So, hydrogen gas in discharge tubes with the removal of electron, we are getting the hydrogen ion or proton. Discovery of neutrons. At the time of J. Thomson, only two fundamental particles like proton and electron were known. In the year 1932, James Chadwick discovered another fundamental particle called neutron. But the proper position of these particles in an atom was not clear till Rutherford described the structure of atom. And you will study about Rutherford's atom model in your higher classes. Properties of neutrons. Neutron carries no charge. It is a neutral particle. It has mass equal to that of a proton, that is 1.6 into 10 to the power of minus 24 grams. Let's see the properties of fundamental particles. What are the fundamental particles? They are electron, proton and neutron. First, electron. It is represented by the letter E, and the mass of the electron is 9.1 into 10 to the power of minus 28 grams, and the charge of the electron is minus 1. Next, proton. It's denoted by the letter small p, and the mass of the proton is 1.6 into 10 to the power of minus 24 grams. And the charge of the proton is plus 1. Next, neutron is denoted by the letter small n. The mass of the neutron is 1.6 into 10 to the power of minus 24 grams. And for neutron, there is no charge, so 0. Among these particles, electron is the smallest one. And the mass of the proton and neutron is equal in an atom. Thomson's atom model. J. Thomson, an English scientist, proposed the famous atom model in the year 1904, just after the discovery of electrons. Thomson proposed that the shape of an atom resembles a sphere having a radius of the order of 10 to the power of minus 10 meter. The positively charged particles are uniformly distributed with electrons arranged in such a manner that the atom is electrically neutral. Thomson's atom model was also called as the plum pudding model or the watermelon model. The embedded electrons resembled the seed of watermelon, while the watermelon's red mass represented the positive charge distribution. The plum pudding atomic theory assumed that the mass of an atom is uniformly distributed all over the atom. Limitations of Thomson's atom model. Thomson's atom model could successfully explain the electrical neutrality of atom. However, it failed to explain the following. Thomson's model failed to explain how the positively charged sphere is shielded from the negatively charged electrons without getting neutralized. This theory explains only about the protons and electrons and failed to explain the presence of neutral particle neutron. Valency. In order to understand valency of elements clearly, we need to learn a little about Rutherford's atomic model here. According to Rutherford, an atom consists of subatomic particles, namely proton, electron, and neutrons. Protons and neutrons are found at the center of an atom called nucleus. Electrons are revolving around the nucleus in a circular path and they are called orbits or shells. This you can see in the given picture. An atom has a number of orbits and each orbit has electrons. The electrons revolving in the outermost orbit are called valence electrons. So in the given picture, how many valence electrons are there in the outermost shell? Yes, there are 8 electrons in their outermost shell. The arrangement of electrons in the orbit is known as electronic configuration. Atoms of all the elements will tend to have a stable electronic configuration. That is, they will tend to have either 2 electrons known as doublet or 8 electrons known as octet in their outermost orbit. For example, helium has 2 electrons in the outermost orbit and so it is chemically inert. Chemically inert means it is stable. There is no need to combine with another atom. Similarly, neon is chemically inert because it has 8 electrons in the outermost orbit. The valence electrons in an atom readily participate in a chemical reaction and so the chemical properties of an element are determined by these electrons. When molecules are formed, atoms combine together in a fixed proportion because each atom has different combining capacity. This combining capacity of an atom is called valency. So valency is defined as the number of electrons lost, gained or shared by an atom in a chemical combination so that it becomes chemically inert. Types of valency. As we saw earlier, an atom will either gain or lose electrons in order to attain the stable electronic configuration. In order to understand valency in a better way, it can be explained in two ways depending on whether an atom gains or loses electron. Atoms of all metals will have 1, 2, 3 electrons in their outermost orbit. By losing these electrons, they will have stable electronic configuration, that is 2 or 8. So they lose them to other atoms in a chemical reaction and become positively charged. Such atoms which donate electrons are said to have positive valency. For example, in sodium atom, the atomic number of sodium is 11 and it has 1 electron in its outermost orbit. And in order to have stability, it loses 1 electron and becomes positively charged. Thus, sodium has positive valency. Look at the picture for better understanding. Okay, there are 2, 3 orbits. In first orbit there are 2 electrons. In second orbit there are 8 electrons. And in third orbit there is only 1 electron. If the sodium loses 1 electron, it will become more stable. All nonmetals will have 3 to 7 electrons in the outermost orbit of their atoms. In order to attain stable electronic configuration, they need few electrons. So they accept these electrons from other atoms in a chemical reaction and become negatively charged. These atoms which accept electrons are said to have negative valency. For example, chlorine atom. The atomic number of chlorine is 17 and it has 7 electrons in its outermost orbit. And in the first and second orbit it has 2 and 8 electrons. So to make it stable, it gains 1 electron and attains stable electronic configuration like inert gas electronic configuration. Thus, chlorine has negative valency. Valency with respect to atoms. Valency of an element is also determined with respect to other atoms. Generally, valency of an atom is determined with respect to hydrogen, oxygen and chlorine. First, valency with respect to hydrogen. Since hydrogen atom loses 1 electron in its outermost orbit, its valency is taken as 1 and it is selected as standard. Valencies of other elements are expressed in terms of hydrogen. Thus, valency of an element can also be defined as the number of hydrogen atoms which combine with one atom of it. In hydrogen chloride molecule HCl, one hydrogen atom combines with one chlorine atom. Thus, the valency of chlorine is 1. Similarly, in water molecule H2O, two hydrogen atoms combine with one oxygen atom. So, valency of oxygen is 2. Let's see valency of some atoms. Molecule hydrogen chloride HCl. So, here the element chlorine's valency is 1 because chlorine is combined with one hydrogen. Next, in water molecule, the valency of oxygen is 2 because oxygen is combined with two hydrogen. Next, in ammonia, the valency of nitrogen is 3 because nitrogen is combined with 3 hydrogen. Next, in methane, the valency of carbon is 4 because it combined with 4 hydrogen. Since some of the elements do not combine with hydrogen, the valency of the element is also defined in terms of other elements like chlorine or oxygen. This is because almost all the elements combine with chlorine and oxygen. Valency with respect to chlorine. Since valency of chlorine is 1, the number of chlorine atoms with which one atom of an element can combine is called its valency. For example, in sodium chloride NaCl molecule, one chlorine atom combines with one sodium atom. So, the valency of sodium is 1. But in magnesium chloride MgCl2, valency of magnesium is 2 because it combines with 2 chlorine atoms. Next, valency with respect to oxygen. In another way, valency can be defined as double the number of oxygen atoms with which one atom of an element can combine because valency of oxygen is 2. For example, in magnesium oxide MgO, valency of magnesium Mg is 2 because the valency of oxygen is 2 here. Variable valency. Atoms of some elements combine with atoms of other elements and form more than one product. Thus, they are said to have different combining capacity. These atoms have more than one valency. Some cations exhibit more than one valency. For example, copper combines with oxygen and forms two products, namely cuprous oxide Cu2O and cupric oxide CuO. In Cu2O, valency of copper is 1 and in CuO, valency of copper is 2. For lower valency, a suffix OUS is attached at the end of the name of the metal. For higher valency, a suffix IC is attached at the end of the name of the metal. Sometimes Roman numerals such as 1, 2, 3, 4 indicated in parentheses, followed by the name of the metal can also be used. Ions. In an atom, the number of protons is equal to the number of electrons and so the atom is electrically neutral. But during chemical reactions, atoms try to attain Stable electronic configuration like triplet or octet, either by gaining or losing one or more electrons according to the valency. When an atom gains an electron, it has more number of electrons and thus it carries negative charge. At the same time, when an atom loses an electron, it has more number of protons and thus it carries positive charge. These atoms which carry positive or negative charges are called ions. The number of electrons gained or lost by an atom is shown as a superscript to the right of its symbol. When an atom loses an electron, plus sign is shown in the superscript and minus sign is shown if an electron is gained by an atom. Sometimes two or more atoms of different elements collectively lose or gain electrons to acquire positive or negative charge. Thus, we can say an atom or a group of atoms, when they either lose or gain electrons, get converted into its ions or radicals. Types of ions. Ions are classified into two types. They are cations and anions. Cations. If an atom loses one or more electrons during a chemical reaction, it will have more number of positive charge on it. These are called cations or positive radicals. Example, sodium atom loses one electron to attain stability and it becomes cation. So sodium ion is represented as Na plus. How? If sodium loses one electron, the number of protons in the sodium atom is more. So it becomes Na plus. Anions. If an atom gains one or more electrons during a chemical reaction, it will have more number of negative charge on it. These are called anions or negative radicals. Chlorine atom attains stable configuration by gaining an electron. Thus, it becomes anion. Chlorine ion is represented as Cl minus because the number of electron is more when compared to the proton in the chlorine atom. Different valent ions. During a chemical reaction, an atom may gain or lose more than one electron. An ion or radical is classified as monovalent, divalent, trivalent, or tetravalent when the number of charges over it is 1, 2, 3, or 4 respectively. If the ion carries one ion, it is monovalent. If the ion carries two charges, it is divalent. If the ion carries 3, it is trivalent. If the ion carries 4, it is tetravalent. Based on the charges carried by the ions, they will have different valencies. Next, valency of anions and cations. The valency of anion or cation is a number which expresses the number of hydrogen atoms or any other monovalent atom like sodium, potassium and chlorine, which combine with them to give an appropriate compound. For example, two hydrogen atom combines with one sulfate ions to form sulfuric acid. So, the valency of the sulfate ion SO42 minus is 2. One chlorine atom combines with one ammonium ion NH4 plus to form ammonium chloride NH4Cl. So, the valency of NH4 plus is 1. Valencies of some anions. First, in the compound HCl, hydrochloric acid, the name of the anion is chloride, and the formula of the chloride ion is Cl minus, and the valency of anion is 1, because the chloride ion is combined with one hydrogen atom. Then in sulfuric acid, the name of the anion is sulfate, and the formula for the ion is SO4 2 minus, and the valency of the sulfate ion is 2 because it combines with two hydrogen atoms. Next, in nitric acid, HNO3, name of the anion is nitrate, and the formula is NO3 minus, and the valency of nitrate ion is 1 because it combined with one hydrogen atom. Next, in carbonic acid, H2CO3, name of the anion is carbonate, and the formula of the anion is CO3 2 minus, and the valency of the carbonate ion is 2 because it combined with two hydrogen atom. Next, in phosphoric acid, name of the anion is phosphate, and the formula of anion is PO4 3 minus, and the valency of anion is 3 because it combined with 3 hydrogen atom. Next, in water, the name of the anion is oxide, and the formula of anion is O2 minus, and the valency of anion is 2 because it combined with 2 hydrogen atom. Next, in hydrogen sulfide, the name of the anion is sulfide, and the formula of anion is S2 minus, and the valency of anion is 2 because the sulfate ion is combined with two number of hydrogen atom. Next, sodium hydroxide, the name of the anion is hydroxide, and the formula of anion is OH minus, and the valency of the hydroxide ion is 1 because it combined with the only one sodium. Next, valencies of some cations. The first compound, sodium chloride, the name of the cation is sodium, the formula of the cation is Na plus, and the valency of cation is 1 because it combines with only one chlorine atom. Next, potassium chloride. Name of the cation is potassium, and the formula of cation is K plus, and the valency of cation is 1 because it combined with only one chlorine atom. Next, ammonium chloride. The name of the cation is ammonium, and the formula of cation is NH4 plus, and the valency of cation is 1 because it combined with only one chlorine atom. Next, in magnesium chloride, name of the cation is magnesium, and the formula of cation is Mg2 plus, and the valency of cation is 2 because here the magnesium ion is combined with two chlorine atom. Next, in calcium chloride, name of the cation is calcium, and the formula of cation is Ca2 plus, and the valency of cation is 2 because the calcium ion is combined with two chlorine atom. Next, in aluminum chloride, the name of the cation is aluminium, and the formula of cation is Al3 plus, and the valency of cation is 3 because the aluminium ion is combined with 3 chlorine atoms here. Chemical formula or molecular formula. Chemical formula is the shortened notation of a molecule or compound. It shows the actual number of atoms of each element present in a molecule of a substance. Certain steps are followed to write down the chemical formula of a substance. Step 1. Write down the symbols of elements or ions side by side so that the positive radical is on the left and the negative radical is on the right hand side. In step 2, write the valencies of the two radicals above their symbols to the right in superscript, and the signs plus and minus of the ions are omitted. Reduce the valencies to simplest ratio if needed. Otherwise, interchange the valency of the element or ions. Write these numbers as subscripts. However, one appearing on the superscript of the symbol is omitted. Let us derive the chemical formula for calcium chloride. Step 1. What should do in the step 1? Write the symbols of calcium and chlorine side by side. For calcium Ca and for chlorine Cl. The negative radical is on the right hand side and the positive radical in the left hand side. Next, write the valencies of calcium and chlorine above their symbols to the right. Here the valency of calcium is 2, so write 2 in the superscript. Then Cl it is 1. Next, in step 3, interchange the valencies of the element. So the 2 goes to chlorine atom and the 1 goes to calcium atom. If 1 appearing on the superscript of the symbol, it is omitted. So thus the chemical formula for calcium chloride is CaCl2. Naming chemical compounds. A chemical compound is a substance formed out more than one element joined together by chemical bond. Such compounds have properties that are unique from that of the elements that formed them. While naming these compounds, specific ways are followed. In naming a compound containing a metal and a non-metal, the name of the metal is written first and the name of the non-metal is written next after adding the suffix IDE to its name. See for example, sodium chloride, NaCl. Here sodium is the metal and chloride is the non-metal. Chlorine is the non-metal. So first we have written the metal name sodium and following that the non-metal chlorine with the suffix IDE. Next, AgBr, silver bromide. Here silver is the metal and bromine is the non-metal. So we have written that silver bromide. In naming a compound containing a metal, a non-metal, and oxygen, name of the metal is written and name of the non-metal with oxygen is written next after adding the suffix ATE for more atoms of oxygen or ITE for less number of oxygen atom to its name. Examples. The first one, sodium sulfate. Here, sodium is the metal, so it is written first. Then sulfur is the non-metal with 4 oxygen atom. So we are writing sodium sulfate because the sulfur is having 4 number of oxygen atoms. So we are using the suffix ATE. So sodium sulfate. Next, in sodium nitrate, sodium is the metal and nitrogen is the non-metal with 2 oxygen. So we are writing sodium nitrite because here the nitrogen has less number of oxygen. So we are using the suffix ITE. Next, in naming a compound containing 2 non-metals only, the prefix mono, di, tri, tetra, penta, etc. is written before the name of the non-metals. See here examples. The sulfur dioxide, SO2. Here both the sulfur and oxygen are non-metals. So here only one sulfur, so no need to write the mono. Next, but in the oxygen there are 2 number of atoms. So sulfur dioxide, 2 oxygen, so dioxide. Next, in N2O5, dinitrogen pentoxide. So 2 nitrogen is there, so dinitrogen. And 5 oxygen is there, so pentoxide. 5 means penta. So dinitrogen pentoxide. Chemical equation. A chemical equation is a shorthand representation of a chemical reaction with the help of chemical symbols and formulae. Every chemical reaction has 2 components, reactants and products. Reactants are the substances that takes part in a chemical reaction, and the products are the substances that are formed in a chemical reaction. So the steps in writing the skeletal equation. Before writing the balance equation of a chemical reaction, skeletal equation is written. The following are the steps involved in writing the skeletal equation. The first one, write the symbols and formula of each of the reactants on the left hand side, LHS, and join them by plus sign. Then follow them by an arrow, which is interpreted as gives or forms. Next, write on the right hand side in the RHS of arrow the symbols and formulae for each of the product. Then, if the product is a gas, it should be represented by upward arrow, and if it is a precipitate, it should be represented by downward arrow. Example, magnesium plus sulfuric acid gives magnesium sulfate and hydrogen gas. So here the magnesium and sulfuric acid are the reactants. Two reactants with the plus sign. So after reacting, it gives. Gives means it's represented by the arrow. The arrow represents which forms or gives. Okay, magnesium sulfate and hydrogen. Here magnesium sulfate and hydrogen are the product. Okay, and then the hydrogen gas is represented by the upward arrow. That means the hydrogen is the gas here. Okay, so the equation thus written is called as skeletal equation, the unbalanced equation. Okay, balancing chemical equation. According to law of conservation of mass, the total mass of all the atoms forming the reactants should be equal to that of all the atoms forming the products. This law will hold good only when the number of atoms of all types of elements on both sides is equal. A balanced chemical equation is one in which the total number of atoms of any element on the reactant side is equal to the total number of atoms of that element on the product side. There are many methods of balancing a chemical equation: trial and error method, fractional method, and odd number even number method are some of them. While balancing a chemical equation, following points ought to be borne in mind. The first one, initially the number of times an element occur on both sides of skeletal equation should be counted. Then an element which occurs least number of times in reactants and product side must be balanced first. Then elements occurring 2 times, elements occurring 3 times, and so on in an increasing order must be balanced. When 2 or more elements occur same number of times, the metallic element is balanced first in preference to non-metallic element. If more than one metal or non-metal is present, then a metal or non-metal with higher atomic mass is balanced first. To find out the atomic mass, we should refer the periodic table. Next, the number of molecules of reactants and products are written as coefficient. Then the formula should not be changed to make the elements equal. Fractional method of balancing must be employed only for molecule of an element like oxygen, hydrogen, ozone and phosphorus, and not for compound like water, ammonia, HCl, etc. Now let us balance the equation for the reaction of hydrogen and oxygen which gives water. First, we should write the word equation. In step 1, we are going to write the word equation. Hydrogen plus oxygen gives water. Next, in step 2, we are going to write the skeletal equation. So what is the symbol for hydrogen is H2, and what is the symbol for oxygen is O2, and what is the symbol for water? It is H2O. So hydrogen plus oxygen gives water. H2 plus O2 gives H2O. Step 3. Select the element which is to be balanced first based on the number of times an element occurs on both sides of the skeletal equation. So here the number of times hydrogen appeared on both sides is 2. Okay, so in the left hand side is 2 and the right hand side is also 2. And what about oxygen? In the left hand side it is 2 and the right hand side it is 1. Okay, next in the step 4, both elements occur one time each. So here the preference must be given to oxygen because it has higher atomic mass when compared to hydrogen. So we are going to balance the oxygen first. Step 5. To balance oxygen, we should put 2 before H2O on the right hand side, because in the left hand side there is 2 oxygen. So to balance that, we should put 2 in front of the hydrogen. So 2 oxygen in the right hand side and 2 oxygen in the left hand side. Next we are going to balance the hydrogen. So how to balance the hydrogen here? See, in the right hand side there is 4 number of hydrogen. Okay, 2 into 2 there are 4 number of hydrogen. So to balance that, we should put 2 in front of the hydrogen in the left hand side. So 2 hydrogen and oxygen gives 2 H2O. Okay, so hydrogen, the number of hydrogen in the left hand side is 4 and the number of oxygen is 2. And at the same time in the right hand side, the number of hydrogen is 4 and the number of oxygen is 2. Now on both sides, number of hydrogen atom is 4 and oxygen atom is 2. Thus the chemical equation is balanced. Information conveyed by a balanced chemical equation. A balanced chemical equation gives us both qualitative and quantitative information. It gives us qualitative information such as the names, symbols, and formula of the reactant molecules taking part in the reaction and those of the product molecules formed in the reaction. We also get quantitative informations like the number of molecules or atoms of the reactants and products that are taking part in the reaction. However, a chemical equation does not convey the following: physical state of the reactants and the products, heat changes like heat liberated or heat absorbed accompanying the chemical equation, conditions such as temperature, pressure, catalyst, etc., under which the reaction takes place, and the concentration, whether it is diluted or concentrated, of the reactants and products, and the speed of the reaction. Laws of chemical combinations. By studying quantitative measurements of many reactions, it was observed that the reaction taking place between various substances are governed by certain laws, and they are called as the law of chemical combinations. And they are law of conservation of mass, law of constant proportion, law of multiple proportions, Gay-Lussac's law of gaseous volumes. In this lesson, we will study about the first two laws, and you will study about the law of multiple proportions and Gay-Lussac law of gaseous volume in Standard 9. Law of conservation of mass. The law of conservation of mass, which relates the mass of the reactants and products during the chemical change, was stated by a French chemist Lavoisier in 1774. It states that during any chemical change, the total mass of the product is equal to the total mass of the reactants. In other words, the law of conservation of mass means that mass can neither be created nor be destroyed during any chemical reaction. This law is also known as law of indestructibility of mass. To know this, we are going to do an activity. We are going to prepare the 5% of calcium chloride, that is 5 gram of calcium chloride in 100 ml of water, and sodium sulfate solution separately. And we are going to take some solution of sodium sulfate in a conical flask and some solution of calcium chloride in a test tube. Next, we are going to hang the test tube in the conical flask and weigh the flask with its contents. Now, we are going to mix the two solutions by tilting and swirling the flask. Next, we are going to weigh the flask after the chemical reaction is occurred. What's the observation? It can be seen that the weight of the flask and the contents remains the same before and after the chemical change. Hence, it is proved that during a chemical change, the total mass of the matter remains the same. Next, consider the formation of ammonia in Haber process from the reaction between nitrogen and hydrogen. Okay, in Haber process, 28 gram of nitrogen and 6 gram of hydrogen gives 34 gram of ammonia. So here, what is the total weight of reactants? 28 plus 6, it is 34 gram. Now, what is the mass of the product? The ammonia, it is 34 gram. So during Haber process, the total mass of the reactant and the product are exactly same throughout the reaction. Now it is clear that mass is neither created nor destroyed during physical or chemical change. Thus, law of conservation of mass is proved. Law of constant proportions. Law of constant proportions was proposed by the scientist Joseph Proust in 1779. He states that in a pure chemical compound, the elements are always present in definite proportions by mass. He observed all the compounds with two or more elements and noticed that each of such compounds had the same elements in same proportions, irrespective of where the compound came from or who prepared it. For example, water obtained from different sources like rain, sea, well, and river will always consist of the same two elements, hydrogen and oxygen, in the ratio 1:8 by mass. Similarly, the mode of preparation of compounds may be different, but their composition will never change. It will be in a fixed ratio. Hence, this law is also known as law of definite proportions.